All right. Well, let's go ahead and get started. Welcome everybody to the third webinar in our series of four um, for the Spatial Stock Assessment Simulation Experiment that you now are all quite familiar with. Today we've got three teams that will be presenting work that is ongoing. It's in progress, so it's a progress update of sorts, see where they're at, investigate some of the things that they've been working on, struggling with, etc. So we're real excited. We have a team from ICES and in particular the Spanish Institute of Oceanography, who will start us off um, using stock synthesis as a modeling framework. They're going to go first, and then after them, we've got a team that's using Gadget. After that, we do have a longer schedule today than the other ones, so after the second team, we will take a little break. Just so everybody knows, we will have a break today, a short break at least to get up and stretch or use the restroom or what have you. And then the third team we have today is working with Castle 2 as a framework. And that one will be interesting because it'll be the first team that's presenting on the use of the Antarctic toothfish simulated data set. So the others have so far been presenting on yellowfin tuna. And so that will be the first one with a different data set. So some interesting nuances there. I did want to also just mention that the fourth webinar that we have is scheduled for January 4th, just after the new year. I'll send out a reminder to everybody on that when that is, about a week early. But I just wanted to announce that here because a week early is right during the holiday time, and sometimes emails and notifications such as that, get lost at that time of year. So just put reminder that that's coming up. Teams that will be presenting then are folks taking a spatiotemporal approach to their assessment model, as well as a team called SPASM, who is working with, it stands for Spatial Processes and Stock Assessment Methods. It's a little bit more of a research-based program or software that's used, and they will be presenting also on the 4th. So we've got those coming. Lastly, an announcement, just a reminder that our in-person workshop is scheduled for March 5th through the 7th. That's in Wellington, New Zealand, and we are real excited to finally be able to have that, which is really important because that's the culmination of getting all of our teams together. These webinars are great, and they're kind of greasing the wheels, if you will, towards that workshop, but we really think that's where we're going to collectively be able to make some progress. So we're really hoping people are going to be able to attend that. There will be remote connection as well for those that can't. So just keep that in mind. Regarding the workshop, I will be sending out a tentative agenda to everybody, so you have a little bit more of an idea of what exactly we'll be doing there. But in short, we're going to be talking with the participants and perhaps some other presentations as well, and a lot of discussion. As well as the attentive agenda, I'm going to send out a Google form to you all just to kind of gauge travel plans to be there, folks that want to participate but can only do remotely, and things such as that. So keep a lookout for those. Those are going to be coming out shortly within the next week or so. All right, I think that's all the announcements I had and the intro. So let me go ahead and introduce the first team today, which is the team from the ICES region, in particular the Spanish Institute of Oceanography. They're going to be using SS3. We have two presenters. They're going to split their talk in half. The first is Francisco Izquierdo, and then also Giancarlo Correa. Francisco has a degree in marine sciences from the University of Alicante in Spain, and a master's in biostatistics from the University of Valencia, where he worked on species distribution by fitting Bayesian spatio-temporal hierarchical models. Currently, he is a PhD student at the Spanish Institute of Oceanography, working on stock assessment, and spatiotemporal distribution modeling. Fran has been doing stock assessment since 2020 and has primarily worked with the IC's South Atlantic hake stock using a sex-separated stock synthesis model. So Fran's going to be doing the first half of their presentation, and then the second half is going to be by Giancarlo, and he is a fisheries biologist with a master's of science in studies of applied mathematics from the San Marcos National University in Peru. Giancarlo worked at the Marine Instituto of Peru, where he investigated the population dynamics and spatial ecology of small pelagic fishes in the northern Humboldt current system. He received his PhD from Oregon State University, where he investigated the impacts of climate on fish somatic growth using population dynamic models. And currently, Giancarlo is a postdoctoral fellow at the University of Washington in Seattle, where he is developing new approaches to model somatic growth in state space stock assessment models. So with that, Fran, I'm going to hand it over to you to share your screen, and you can go as soon as you're ready.
Okay, can you hear me?
Yes, you sound very clear.
Okay, and can you see the presenting mode?
Yeah, it looks perfect. Thanks.
Okay, cool. Well, thank you for the introduction. I'm Fran, and I'm going to explain you the modeling progress that we have been doing for the yellowfin tuna dataset with stock synthesis. We structured this presentation in 6 steps or points. In the first case, place, we explored the data provided by the project. In the second place, we did a CPU standardization. In the third point, we will see the stock synthesis parameterization and some key or main decisions that we took. In the fourth step, we will see the base models that we achieved and some diagnostics. And in the fifth, we will see the provisional result for 20 assessment models. And at last, we will see some future steps. Okay, so we explored the provided data. In the case of areas, we can see we have 2 different configurations, the 1 area and the 4 area one. Regarding the catch, what we saw is that area 1 is the one with the higher number of catches, followed by area 4. And if we look at the fleets, Purseine is the one displaying the bulk of the catches, followed by Troll. Well, if we look at the length frequency distribution, similar as we have seen in the catch, the area 1 is the one displaying the higher number of data of length frequency distributions. And regarding the fleets, the Purseine is the one displaying also the higher number of information. What we can see in the right plot, if we look at the distributions by fleet, is that more or less all of the fleets have a range from 50 to 150 centimeters for the yellowfin. And we point here that the long line seems to be the fleet catching the bigger individuals. Okay, so here we also analyze the 221 data set, and we made this discretization of different ranges for small, medium, and big individuals. And if we look at the left plot, we can see that the smaller individuals are targeted by Purseine, and they are mainly located in area 1 and area 4. And regarding the long line fishery for the bigger individuals, we can see that they are found in area 1, in area 2, and in area 4 mainly. Okay, regarding the tagging data, we know that all of the tags were made in the area 1, and all of the recaptures were done by Purseine mainly in area 1, followed by area 2, and a bit of them in the area 4. Okay, So regarding the CPU standardization, as our aim is to fit a spatial stock assessment model, we thought that it would be very important to take into account the spatiotemporal autocorrelation in the abundance indices, or in the CPUE in this case. So what we did was to fit 3 different Bayesian spatiotemporal models with INLA. And well, you have here the 3 models. In the first case, we have the random effects model. This is not a truly spatial effect or model, but we have this random effect for each one of the cells in the study area. So we are somehow taking into account the differences in the variability among them. We also included, as in the rest of models, a smoothed effect trend for the pseudo-GR variable. And well, the second model we tried is the BESAG model. The BESAG model is often used in spatial epidemiology. And this model contains a spatial structure, this component, and also the added smoothed trend. I can explain you a little bit better that the BESAG spatial effect implies that nearby things are similar. So what we do is we construct a neighbor matrix by polygon contiguity in order to create this spatial correlation structure. And we end up with this connectivity diagram that you see here. So this model, this effect is taking into account the spatial autocorrelation. And now we go to the third case, which is the BESAG spatiotemporal model. This one is what we would call a truly spatiotemporal model, because in this case, the spatial effect has an interaction with the time. So in this case, the BESAG structure is interacting with the pseudo-GR variable with an autoregressive process of order 1. Okay, so here we can see the model selection. From the 3 models, the BESAG spatiotemporal was the one providing the lower value of the indicators, so the one showing a better goodness of fit. But also it was the one showing the most time consumed, as you can see, by a high difference. I think this one is around from 2 to 3 hours, more or less. So this was the best model. Here, just to mention that to get the final prediction of the CPUE, we just sum the predicted values in the different cells by area in each one of the pseudo-GRs. So we end up, for instance, for the 4-area case, with these 4 scale indices. And for the 1-area case, you have here the single area prediction. Here, just to point in the orange and black one, which are the BESAG and the BESAG only spatial and the random effect model, give a very similar trend. And the BESAG spatiotemporal, the blue one, is the model giving a bit different trend respect to the others. Well, so here, if you look at this map, what you can see is the spatiotemporal prediction of this BESAG spatiotemporal model. And we can infer, or we can see how the relative abundance is moving in our study area along the time. From here, it's clear that the area 1 and 2 are the most abundant areas, and the area 3 and 4 are the less abundant one, and more similar between them. Here, just to make the difference, to explain a little bit, if we think in the 2 first models, they only have a single spatial effect, or in the case of the BESAG model, for instance, a single spatial effect, so a single map for all model GRs or pseudo GRs. But in this case, the spatiotemporal model contains a random field for each of the GRs, and they are connected with an autoregressive one time correlation parameter. So we think this is an important thing to take into account when modeling these type of indices. Okay, and now the third point regarding the parameterization of stock synthesis and the key decisions. We did the 1-area and 4-area model configurations, but inside of them, we tried two different configurations, the pseudo-GR1 and the GR1. The pseudo-GR1, the idea is to build a fine scale model with all of the provided information in the experiment. So this means from 0 to 28 pseudo-GRs, seasonal caveats, etc. And in the GR case, we wanted to build a model, we can say a more simplistic model in terms of the parameter inputs, trying to emulate what we would have in a real case situation. So we are using only a K-base, for instance. Well, I will explain it a bit better here. Regarding the biology, the pseudo-GR model, as I said, we just input the parameters as provided. So as you can see here, for the pseudo-ages or pseudo-GRs, you have a really good informed model. But in the case of the GR, for the natural mortality, we did the sum across seasons for each age. So we end up with these 7 values. Regarding the maturity, we did the average value across seasons. And regarding the K, we just input the 0.45 K-base. For the Spanish relationship, we just fix all parameters as were provided and leaves are 0. And for the growth, we also fix all of the parameters as were provided. Okay, and now we will see a bit on the key decision or the important decisions that we took when building the models. In the talking about the recruitment, for instance, in the pseudo-GR model, for the 1-area and 4-area models, the recruitment takes place in each of the seasons. I mean, seasonally. So in each of the pseudo-GRs is settled. But in the GR case, as we have a seasonal configuration, we could play a little bit more with this. We tried different options, but in the end, in the 1-area model, we estimated settlements in the months 1, 4, 7, and 10. So would be equivalent or seasonal as the pseudo-GR. But in the 4-area model, as a first approach, as is a complex model with all of movement parameters and stuff, as we will see now, what we did was to set only recruitment settlements in the area 1, and we settled them in the beginning and in the middle of the year, as we think this will catch somehow this variability along the year. And also we set a time varying effect on July, on the second settlement, to allow the model to change the proportion of the estimated proportion of recruits along the time. Regarding the recruitment deviation, the advanced parameters, what we did in both models was to run the model with Hessian in order to get the stock synthesis suggestions. And then we input these suggestions again in the models. An important decision that we made here was to change the early GR no bias adjustment parameter from the value suggested of 9050 from SS to 9070, because we saw that in 9070 is the period when we start to have more information on length distributions coming from the fleets. So in this case, I think in 9050 we had information on one fleet only, and in 9070 we started to have around 4 fleets providing length frequency distributions. Okay, regarding the selectivity, for both cases, pseudo-GR and GR, we tried selectivity at age and selectivity at length configurations. Our hypothesis was that selectivity at age may work better in a pseudo-GR model because there is not a huge difference in growth across the pseudo-ages, we could say, and it would work worse for the GR model, right? So finally, this is what happened. We selected the selectivity at age for the pseudo-GR model. And in the case of the GR model, the selectivity at length was giving a best performance. Well, regarding the selectivity of the fleets, we set all of them double normal unless the long line. And in the 4-area case, at the beginning, we tried to estimate different selectivities for all of the fleets. In the 4 areas, the fleets across the different areas, at first, they are different. But what we saw is that for fleets like Purseine, which is the one that is catching all of the sizes of the fish, it was not making sense that in the area 1 the selectivity was logistic, and then in the area 4 the selectivity was double normal. So following this and trying to start with a simplistic model, we just mirrored all the selectivity parameters of the same fleets across areas. It's true that we also think for a fleet like the one called Others, that is a mixed fishery, it could be interesting to try to let the model estimate different selectivities in the different areas, but this is something to explore. Okay, and now regarding the tagging data, following the manual, we just auto-generated all the tag parameters, and we realized that the model was not capable of estimating all of the tag parameters. So what we decided was to take information from the references that appeared in the real report, the assessment report of the stock, which are the initial tag log parameter that we fix in a 10%, the tag logs chronic, what we fix in a 3%, and the mixing latency period that we try some values, checking on the observed and expected model fitting. And in the end, I think we end up with the value of 3 seasons. Now, talking about the movement, we have information about the movement from tagging data. We know that the fish is tagged and recaptured in area 1 to area 1, area 1 to area 2, and area 1 to area 4. But what happened with the area 3? Because it's not connected with the rest of them. We have here some ideas or points. The first one would be that the CPU spatiotemporal maps that I showed you before indicate that the area 3 and area 4 are more similar in terms of relative abundance. So this could be a good connectivity. Also, that the CPU is a scale, as I mentioned in the previous slides. So we could assume a constant catchability parameter. And we think that this will help also the model to properly estimate the movement, right? And the third point is that we are assuming that all of the recruitment is taking place in area 1 by now. And if the individuals get out from area 1, they must come back for reproduction. So with these ideas, we defined the movements between area 1-2, area 1-4, and area 4 and 3. Okay, so now about the base model and diagnostics. As we said before, we have the 1 and 4 area configurations, and we wanted to highlight that we tried the 2 options, the original CPUE, the provided CPUE, and the spatiotemporal Bayesian CPUE. I have to say that in both cases, we saw a good performance across the different configurations regarding the retrospective analysis or the diagnostics. But in the end, we decided to select or to focus on the spatiotemporal model configurations because the CPU is taking into account the spatiotemporal autocorrelation. So here I'm presenting you the summary of the base model of one area in the JR configuration. This model includes the CPU spatiotemporal, the 4 settlements, the selectivity of Purseine longline and others is estimated as logistic, but we think this is nothing to, it's not a big assumption. I mean, it's fine by now. And I have to say that the tagging data in the in this model, in the year configuration, without the tagging data, the model was not capable of estimate the F scale. We tried different things, but in any of the cases, the model was estimating an F higher than 0.05 or something like that for the whole time series. So in this case, the tagging data is making a big impact. So it's informing on the fishing mortality, especially on the purseine fleet. And it's helping, it seems it is helping the model to properly estimate the F and to get a lower biomass, right? Regarding the retrospectives, we can see that this model have a good retrospective pattern unless the retro or the pill number 5, that is a bit out of the intervals. And it happened the same with the retros for the index, for the CPV. I don't know if I'm talking too fast, I'm sorry. So here we have the base model of 4 areas in year configuration. And well, the settings of these models are the CPU spatiotemporal, the shared catchability parameter across all of the areas. As I mentioned before, the settlements only in area 1 with with settlements in the first and the 7th month. We input also the movement definitions. And again, that I have here in red, it happened the same with the tagging data. In the 4 area model, without tagging data, the model was not estimating an F higher than 0.05 or something like that. And here, I think I forgot to mention something that is good for discussion, is interesting. In the tagging data, we have the mixing latency period parameter, which is a parameter that is telling us how many seasons needs a target fish to be recovered with equal probability in the whole area, right? So in the case of the 4 areas, this parameter is fine. I mean, it's informing the model properly because the model knows that, for instance, in area 3, there is no tagging data. So the model is able to identify in which area we are tagging and recovering. Just to mention that in the 1 area model, we are assuming this bias because this model is considering the whole area as a single one. So it's assuming that the fish can be equally found in the whole area. So just mention this. Here we can see that the retros from this 4 area model are fine for the SSB and also for the indices. And I think I'm done. Now Giancarlo will present the pseudo-GR configuration. I will stop sharing.
Okay, I am already sharing my screen, so let me know if you cannot see it yet.
Looks good, Giancarlo.
Okay, great. I will keep my camera off because just to save some internet. I have been having some problem with my internet. So I will keep it off. Okay, Joe, I am going to present the section about the pseudo-GR configuration. As Francisco mentioned, that this is a work in progress. We are still discussing a couple of things about the configuration that we are using, and we are starting to understand what are the reason of the differences between the both configurations. Okay, so this is some figures like summaries, some summary figures about the pseudo-GR configuration. One of the things that we had some problems to understand at the beginning was about the parameterization of somatic growth. Especially, we were not sure about what the mean lead at age 0 should be, and and also we were not sure if that is important because the age 0 is not part of the population yet because the settlement occurs at age 1. So the model right now is the configuration of the model right now is in this way. So the model is assuming that the mean length at H0 is the same as the mean length at H1. So it's 22 centimeters. And some of the things that I would like to discuss at the end of this presentation is that if other groups have a similar configuration like this one, and if this is important again, because I don't know what are going to be the impacts of this kind of configuration. For H1 and older edges, the mean length at H is very, very, very similar to the information provided. So we are pretty confident about the mean length at H 1 and older for this configuration. Okay, so for the selectivity, as Francisco said, we tried two different kind of selectivity at age and selectivity at length. We didn't find explicit information about what kind of selectivity we should use for this model. So that's why we wanted to try two different selectivities for both configurations. And Francisco said, like for the GR configuration, it was hard to include the selectivity at age because in that configuration, there are only 7 edges. So in our opinion, I think there is not enough information to estimate a good selectivity for that configuration because we only have 7 edges and there is no resolution. So for that reason, in the GR configuration, we use the selectivity at length. However, for this configuration, we kept the selectivity at the age because if we see the fits for the selectivity at length and selectivity at age, we are going to find that the residuals are smaller for selectivity at age. And this is one of the things that we want to discuss here. This is for the one area model. In Francis, in a paper by Francis 2016, I think, or 2014, I don't remember right now, he mentioned that in most cases, the selectivity should be at length or length-based. However, he also mentioned that in some cases, when there is movement between areas, in those cases, the selectivity at age could be the best option. So that's something that we have no clear, we don't have the reason very clear right now. It's like why the selectivity at age is performing better in this case for the one area model instead of the selectivity at length. Because there is no movement here, so we expected to see a better performance for the selectivity at length. So yeah, that was one of the results that we got, and maybe it could be important to discuss it at the end of the presentation. Okay, now one of the other things that we are also discussing right now is about the effects of the tagging data for the one area model. Before starting this workshop, we understood that the tagging data is important because it provides information about the movement between areas. And for us, that was the main information that that kind of data provides. However, for the one area model, we don't have movement, we don't have areas. So one of the things that we are still discussing is about why the tagging data is important for the one area model. And as Francisco said as well, like one of the things that we believe that this is the tagging data is providing information is about the fishing mortality or the mortality in general. However, since we have the natural mortality fixed, in this case, the fishing mortality is the mortality section that is varying, is changing. So this is a comparison between the spawning biomass for the one area model, including the standardized CPUE without tagging data, and the one area model with standardized CPUE, including the tagging data. And as you can see, there is a big difference in the spawning biomass here. If we don't include the tagging data here, we have very huge spawning biomass over years. But when we include the tagging data, it looks like the spawning biomass is better, talking about the scale. And we see the fishing mortality as well. We are going to see that the fishing mortality gives more a better estimate when we include the tagging data. So that's one of the another point that we want to discuss is about what information provides the tagging data when we only have one area model. It's something that we want maybe to understand better. About the diagnostics, we didn't see like super bad patterns for the residuals. These are the residuals. What we observe, however, is some consistent negative residuals for the beginning of the time period here. This was the only strange or weird pattern that we found for the CPU residuals. And we believe that what is causing this is that we are estimating the recruitment deviates starting from 1G, I think it was 1972 or something like that. So we believe that if we start to estimate recruitment deviates before that year, we are going to fix these residuals here. And the reason why we are starting to estimate recruitment deviates in that year is because we are starting to have lane compositions in that year or so. So in this case, for this configuration, for this model, the lane composition is an important input to provide information about the recruitment deviates, in your opinion. So that's why we are estimating, or we are starting to estimate the recruitment deviates from that year. And that's something that we would like to discuss as well at the end of the presentation. If that's a correct assumption, we should start to estimate recruitment deviates when we start to have good data, or we can start to estimate deviates before that year. Okay, cool. And these are some retrospective patterns. This is the retrospective analysis that we did for the one area model. For the case of the Monroe index, we got a pretty good index that's saying that there are no weird retrospective patterns here. However, for the predictive scale of the model, this is an index that is telling me information about the predictive scale of the model. We are not getting good result for this index. We expect to have this index smaller than 1. However, this index is pretty large. And we see the plot here, we're going to find that the predictive scale is going to be pretty bad if we remove years of data for the CPU in this case. There's going to be always a negative, a bias here when talking about the predictive scale of the model. Okay, for the full area model, again, this configuration is pretty similar. In this configuration, when we include a standardized CPU, we include also staging data, movement, and recruitment between areas. I think this plot is pretty clear already. For this case, we also use the selectivity at age. And again, we run some diagnostics for these runs. We didn't find weird pattern for the residuals for the index, except for the early years. And I think that what is causing these negative residuals is the recruitment estimates that we are assuming, and also the residual for the mean length each fishery. And similarly here, the Monroe index was pretty good, so we didn't find a retrospective pattern here. And also the predictive scale for some indices were pretty bad, especially for the index 1 or for the CPU 1 or for the CPU 4. Okay, then the analysis that we performed was the cross-check sort production model. In this case, we use the SPIC model, which is a stochastic sort production model in continuous time. For this model, the input data is going to be cache data in tons. And we use the cache data and original CPU as well, but also we included the spatial temporal CPU, the standardized CPU that we use for the configuration that we showed. And then I move the results here. These are the results of the sort production model. As you can see here, the red line is the results of this surplus production model, and we have four different the results for all the configuration that we just showed. This is a result that is still in progress because we want to do this analysis for all the replicates. This plot is just showing the result for the first replicate. It's only for a single replicate, so maybe it's still too early to get conclusion from this analysis. But what we can see here is that the one area model, which is the green line and the blue line, are pretty similar to the SPIC model, to the surplus production model, as you can see here. But for the 4-area model, we got different results for the GR configuration and pseudo-GR configuration. The purple line here is estimating higher biomass than the SPIC model, and the GR configuration is estimating lower biomass than the SPIC model. So, as I said, I think it's still too early to get conclusion from this analysis. Hopefully, we are going to present the final results in the next meeting. And then we ran some provisional 20 assessment considering 20 replicates for the 1-area model. These are the results for the 1-area model. And we are showing here all the runs that we have for the fishing mortality and the spawning biomass. And this first column is for the pseudo-GR. PY means pseudo-GR, and the Y means like GR configuration. This is for 20 replicates as some provisional results. And what we can see here are that the spawning biomass trends over time are pretty similar for both configurations. However, there is a small difference in the scale between the pseudo-GR configuration and the GR configuration. I think the spawning biomass is a little bit smaller for the pseudo-GR configuration compared to the GR configuration. And again, we got some kind of descriptive statistics for these runs. Maybe the most important one is the percentage of convergent runs. For the GR configuration, we found 85% of convergence. And for the pseudo-GR configuration, we found around 95%. And again, it looks like the CV for the spawning biomass, fishing mortality, and recruitment is a little bit higher for the pseudo-GR configuration compared to the GR configuration. And these results are for the 1-area model, and these results are for the 2-area model. Again, the temporal trends in spawning biomass and fishing mortality are pretty similar. However, the difference here is that the spawning biomass for the pseudo-GR configuration in this case is a little bit higher compared to the GR configuration. And also, we can observe that the variability among replicates are larger for the pseudo-GR configuration compared to the GR configuration. This is the percentage of convergent runs. For the GR configuration, it was 75%, and for the pseudo-GR configuration, it was 90%. Okay, they were the results that we have so far. As I said, we are still exploring other configurations, and we are discussing the results. We are starting to understand what are the reasons that is driving the differences between the GR configuration and the pseudo-GR configuration. So these are only a few points that we want to mention before finishing this presentation. We want to keep exploring the trial without tagging data. As I say, one of the things that we want to understand and we want to make sure is that what information is providing the tagging data, especially for the 1-area model. We want to try different recruitment settlement settings in the 4-area model. Especially what happens if we don't have tagging data in the model. We want to see if the model is able to estimate recruitment among areas without the need of using tagging data or estimated movement parameters. Explore different movement settings in the 4-area model. Francisco already said the configuration that we use. However, we are aware that there are other configurations that could be suitable for this experiment. So that's something that we are already exploring. Compare and discuss the difference between both configurations. Compare and discuss the difference between the 1-area and the 4-area configuration. Just to understand what happens if we ignore the spatial structure in the stock assessment model and we only keep the model in a 1-area configuration. And thank you for your attention. These are the emails of the group, and you can find more information also on these two websites. And thanks.
All right. Thanks, Fran, and thanks, Giancarlo, for your presentation. It was very thorough. And then thanks for staying on time. We do have about 10, 12 minutes for some questions right now. So folks, go ahead and use the raise hand feature and I can call on you. And just a reminder, we'll have 30 minutes at the end of all the presentations for a more broad discussion as well. So I'll just pause a minute so folks can collect their thoughts, but use the raise hand feature. All right, Brian is the quickest with his hand. So Brian, I'm going to go to you first.
Yes. Hi, Fran. First off, I really liked your presentation. We go after you. I feel like you've raised the bar. My question is in relation to the tagging data, particularly for the one area model. You showed that it's affecting fishing mortality estimates. I'm just curious, kind of hearing your thoughts on where that is coming into play. M is being fixed, and wondering if it's kind of alternating a total mortality estimate, and the only thing that can vary is the fishing mortality estimates. That's my thought, maybe out of left field, but curious of your thoughts. Thank you.
Of my thoughts about the fixed parameters, you mean? Or sorry, I didn't get it.
What model parameters are being estimated when you turn tagging on for the one area, and how that translates into what the model is thinking the population's doing?
Well, as I understood from the manual and also from some comments in the forum, the difference is regarding tagging data between the one area model and the 4 area one is that in the 4 areas you can the model knows in which of the areas which fleet is acting in which of the areas, right? So an important difference or an important point is that the initial reporting rate for the fleets is gonna make a big impact on the model, as we saw at the beginning. As in the one area model, if you let the model estimate all the initial reporting rate parameters, is expecting that all of the fleets can report tagging data, and this was making a big impact. This is something that we fixed or we realized just setting the reporting rate for Pursein. And I think I'm not answering your question. I don't know. I'm not sure if I can answer it.
I think Frank, also the question is related to what parameters we estimated related to tagging for the one area model, and I think
we are only estimating the.
Yeah, go ahead.
We are estimating the initial reporting rate and the reporting rate decay. The rest of parameters are fixed by now.
Yeah, and also it's important to say that those parameters are being estimated only for the Pursein fishery, which is the only fishery that we get tagging data.
We also try to let the model estimate in fishery in long line, not only in Pursein, because we thought that long line fishery could be also collecting tagging data. But this is a trial. We have still to keep exploring.
Yeah, and also some of the discussion that we had at the beginning is that if we should keep fixed the parameter for all the other fleets, I mean, all the other fleets except the Pursein, or we should let those fleets also to have estimable parameters. I think what I am trying to say here is that we only have data for the full Pursein fishery, and we wanted to understand what was the reason of that. The reason is because the Pursein fishery is the only fishery reporting tagging data, or because the Pursein fishery is a fishery with the larger catches, and that's why that fishery has a higher probability to report tagging data. And I think, in our opinion, it's important to understand that aspect, because that's going to have some influence in if we fix the parameter for all the fisheries except the pulsane, or we estimate the parameter for all the fisheries as well. That's something that we decided just to keep fixed the parameter for all the fisheries except the pulsane, and only estimate the parameter for the pulsane fishery, because we only have the tagging data for the pulsane fishery. And also another part of your question, I think, was about the natural mortality and fishing mortality. In this case, the natural mortality is fixed. So all the variation and all the changes are directed towards the fishing mortality. That's what we believe. So maybe one of the questions that we also have is that what happens if we estimate the natural mortality? The natural mortality is going to change if we have the tagging data in the one area model. Yeah, and that's something that we don't really know what's going to happen.
All right, thank you very much for your responses. Rick, I see your hand is up. Why don't you go next?
Yeah, thank you, and great presentations. I really like it. One comment I would make is that in the 4-area model and in the 1-area model, for the pursane, because the pursane has such dome-shaped selectivity, that degree of dome-shaped selectivity is really going to interact with the degree to which the tagging data can inform the fishing mortality rates. So that's something I don't think we looked at closely, but definitely dome-shaped selectivities will interact with the inference about Z that comes from the tagging data. And I really like in your presentation that in the 1-area model, you brought out the point that you really need to look at reporting rates for the other fleets. I think that was an important factor to bring to the forefront. Thanks.
Thank you.
Thank you, Rick.
Okay, any other questions or comments? I guess while folks are thinking, I'll ask one. I was curious. Dan has his hand raised. Go ahead, Dan.
Yeah. Can you hear me? Slow internet. Yeah, so I was just interested if you could talk a bit more about kind of your estimated movement rates and whether you had any of the issues that we've seen in some of the previous models about kind of the confounding between recruitment and movement parameters. And, you said you fixed where the recruitment occurred in the spatial model. So I was wondering if that had any kind of a knock-on effects on your movement estimates and things like that. Thanks.
Brian, you want to go ahead with that?
Yeah, can you go to the movement slide? I think it's the next one.
Yep.
Well, the truth is that we haven't explored the interaction between the recruitment and the movement because we just end up with this model like a couple of weeks ago. What we did was just to set the movement definitions that you can see here, and with the recruitment we wanted to explore this interaction by letting the model having recruitment in different areas, not only in area 1, but as a first approach, as we have to define different, like I think around 20, maybe a bit less movement parameter for each recruitment settlement from the source area to the rest of them. Increasing the recruitment areas will also increase quite a lot this number of parameters. So I don't have any by now information on that, but we want to explore it for sure.
Yeah, we also sorry.
Oh no, go ahead. I was just gonna ask if there was any issues estimating movement itself, or what those estimates kind of looked like.
Yeah. Maybe after this, Frank can show the result of the movement. But that we also had a discussion about that question that you made, is especially for area 3, because we didn't have movement or tagging information for area 3. So one of the questions that we had is like, what happened with that area? How the model is going to estimate movement rates to that area if we don't have tagging information for that area? The model is going to estimate a movement parameter, or is going to estimate the recruitment, higher recruitment or lower recruitment for that area. So we want to explore what the model is going to do with area 3, especially about the recruitment and movement. It's going to give more weight to the recruitment, or it's going to estimate a higher movement parameter. That's something that we don't know yet. So, Fran, do you want to show the movement rates that you got?
No, yeah, well, no, but about the movement, well, two things. About what you just said, I have a guess that it's, if we just think on the movement, I think that the fact of having the constant catchability among areas makes somehow, is my guess, we have to explore it, but it's not gonna make a big difference if the connectivity with the area 3 is from area 4 or it's from area 2. I mean, because the model already has knows the level of abundance, or the SSB, that there is in each of the areas. So the movement rate parameters will be estimated to raise that level. That's my guess. That's something that we still have to explore to change the connectivities. And regarding the estimated parameters that you were mentioned, we still have some touching the bounds. It's true that I think was one from your suggestions. We were fixing the resident parameter in 1, and now that we change it to minus 0.25, I think, to an 80-something% of residents, the bounds are, I mean, there are less parameters touching the upper and the lower bounds, but we still have to explore that.
Yeah, I have a little bit of a similar follow-up question, if I can. I was really curious, the difference you had between your one area model. Well, let me start with the similarity with the one area model and the surplus production model that you guys did to as an additional diagnostic or model to run, and then the difference between that set and then your 4 area model, and kind of the difference. Yeah, exactly, the difference in scale. And I can see that arising, with the addition of tagging data and working through all the additional things and potential confounding that movement, recruitment, and things like that interact when you move to a multi-area model. But I was curious if you had any hypotheses about why it's the directional difference between the time component there, right? The single year versus the pseudo year. And do you think that has to do with the way that the year model averaged over the pseudo year values, biological values, or just any other thoughts on that bidirectionality of scale here?
I don't know. I can start with that. I don't know if we can get this conclusion from this experiment yet. As I said, it was only for a single replicate. So we are not sure if for the older replicates, we are going to find the same pattern for this analysis. That's something that we are going to update for the next meeting. Only for this single replicate, we found that this 4-area model with a pseudo-GR configuration had higher spawning biomass in this case. But however, for other replicates, we found that the biomass for the 4-area model pseudo-GR configuration was lower. And that is shown here. For example, if we see all the replicates, we are going to see that the median of the spawning biomass across replicates are going to be a little bit. So my guess is that I think it's still too early to get some conclusion from this analysis. So yeah, actually, I don't know what to say about that question, because I think we need to run more replicates to really understand what is driving this difference in biomass, in the scale of the biomass. I don't know if, Fran, you have some hypothesis about it.
Well, yeah, go for it.
No.
Well, I just going to say, I think that's reasonable. I mean, you could expect variability to be higher, I suppose, in the Fourier model. So waiting to see how those replicates pan out is a worthy thing, because the confidence bounds on there might drastically overlap. So I think that's a good point. I did see one last, maybe Dan raised his hand in response to this question, or do you have something new?
That was it.
Okay, great. Okay, well, let's pause here. Again, there's more time for questions in the 30 minutes at the end. Thanks very much, Fran and Giancarlo, for presenting.
Thank you.
Thanks.
And let's move on to our second presentation today, which is going to be from William Butler. Originally from the United Kingdom, William Butler obtained a PhD from the University of Iceland under the supervision of Gudrun Bartendorsia. The topic of his thesis was modeling the behavior and dispersal of gadoid early life stages. He started his postdoc at the Marine and Freshwater Research Institute in Iceland 2 years ago. He is based in the demersal division, working predominantly with the Gadget modeling framework, which is what he is going to be talking about right now. Will, go ahead and share your screen, and you can get started when you're ready.
Thank you. Let me just get up there. Here we go. Can you see it?
Oh yeah, that looks good, and we can hear you very well.
Okay, great. Yes, hi everyone. My name is William Butler. I'm a postdoctoral researcher at the Marine and Freshwater Research Institute in Iceland. And I'll be presenting on behalf of the Gadget team for the Spatial Assessment Modelling Workshop. So I've been leading the team, and then there's Bjarki Thor Elverson, who's also from the Marine and Freshwater Research Institute, Valerio Bartolino, and Alfonso Perez Rodriguez. So I just want to start by giving you a brief overview of Gadgets. It's a age and length based eco simulator and stock assessment tool. It can simulate multiple fleets, multiple stocks, and multiple areas. So I was asking the rest of the team kind of about experiences with using Gadget in multiple areas, and there's a few examples I've listed here. There's a COD model developed by Lorna Taylor in the early 2000s, and this modeled migration of cod between the north and south of Iceland. There's also the Bormcon region, which is it was developed by Gunnar Stephenson and I can't remember the other name, but anyway, that was the precursor to Gadget, and that was partly a migration model. And then there's also a multi-species, multi-area Barents Sea study looking at interaction between minke whales and cod. My personal experience is I haven't really looked at spatial modeling within the Gadget framework yet, so this is it's going to be a good opportunity to test this out. And I think other studies between the group of us, there seem to be some in-house studies really, but So while the Gadget's capabilities are there, it hasn't been kind of spatial models haven't been developed that much using the Gadget framework. So I'm just going to introduce Gadget 3 now. So this is the latest version of the Gadget framework. It's written by Jamie Lentin at Shuttlethread and Bjarki Thoralvarsson. So the models are written in R, and then they use the TMB to build the objective function. So this is a number of improvements over Gadget 2, many of them relating to the use of TMB, such as automated differentiation, which is it's really improved the kind of optimization speeds of the model. And then there are other benefits, including getting out uncertainty reports for variables, random effects. In general, the framework's highly customizable. What I mean by because you compile the R model, it's very easy to kind of add in custom-made, for instance, like selectivity functions or growth functions. They can just be imported into model very easily. And another benefit over Gadget 2 is that the objective function is mobile, and by that I mean it is compiled and then it can be used with R optimizers, whereas Gadget 2 was predominantly in-house model. So the current status of Gadget 3 is, I mean, the model's pretty much there. So it replicates, say, for instance, if you start off we have a assessment model for Greater Silver Smelt, and if you start the models Gadget 2 and Gadget 3 in the same spot, then they produce the same result. And we've been working on lots of tools to help kind of improve the interface and kind of the capabilities for building models and analyzing your outputs. There's also some areas which we're still working on. For instance, this workshop here is going to be the first chance of using the migration routines and also tagging. And we've also been having some, kind of finding the best way to kind of use the R optimizers. This is still a bit of a work in progress. So I'll just talk about the modeling process. I'll just give a little disclaimer here first, in that we've kind of been battling the single area model at the moment. So we're still not quite there yet. And some, I say, it's just been a bit of a, going around in circles a bit, but I believe we're heading in the right direction. So just in this presentation, I'm just going to kind of tell you what we've been doing, kind of the assumptions we've made, how we've set up models, and then I'll just go through the results of the most recent run. In terms of, so we obviously haven't expanded it to 4 areas yet, or we haven't included tagging data. So we're still focusing, just trying to get this one model up and running. So all the data we imported into MFDB database. So the database is used for kind of processing data for inputs for Gadget and other ecosystem models. And then once that was all ready, we basically just run a kind of out-of-the-box model with Gadget 3. So in this case, growth, maturity, initial bounces, and recruitments, all estimated. It's just kind of get a fix of what the population dynamics would look like. And the next steps kind of looked at this, and then we just sat down and had a discussion about kind of how we're going to set up the model. For instance, we decided, obviously, the growth parameters, we weren't going to estimate them because there's no age data and they're provided. And also just like how we wanted to set up routines and whether or not they should follow the operational model. Key ones, how to set up recruitment. In, say, the typical Gadget approach for modeling recruitment is to use 3 parameters rather than kind of using a stock recruitment curve. So that's the approach we've taken here. And then we just highlighted this here. This is the stage we're basically at. We're kind of fitting and diagnosing the models for the one area. The without tagging data at the moment. So the model structure we've gone with is the initial conditions. They're taken from equilibrium. So we were using a 3 parameter per age group per stock. And we've also tried kind of estimating carrying capacity and then ascribing the numbers at each age based on the proportion and the decay due to natural mortality. But now that we've gone for this approach, so we just spin up the model without any fishing pressure and then take the state at equilibrium. Maturity is length-based, so we just kind of estimated the OGI to fit approximately the data provided, and so this is, and maturity is considered a continual process in this, so at each step. Aging is annual, so we went for the calendar year approach as opposed to the pseudo years. And for many of the, well, for the parameters that vary per age, so the ages were 0 to 2 and 1 to 7. But for the parameters, for instance, K and M, which varied within the seasons per age group, we averaged these across seasons. L infinity was fixed to the operational model one. Yeah, natural mortality was age dependent, average those seasons, and for renewal we just took a 3 parameter per quarter. Fleets, we followed the operational model, so we had 7 fleets, and for selectivity functions we used the 6 dome-shaped, 1 logistic curve, which was the long line, and we also had the survey fleet, which took the selectivity of the long line. So I'm just going to jump straight into the results now. And so this is basically the most recent model we've ended up with, and so we see essays. So the spoiler stock biomass is kind of in the ballpark of where we want to be, and obviously it's heading in the right direction as well. It took a while to get here, mainly because recruitment prior to the period when the CPUE was there, recruitment was normally shooting through the roof. But yeah, so this is working now. And here we see recruitment. So this is per quarter per year. And it's fluctuating up quite a lot, but it's generally above the R0 provided by the model. But we can see how these are basically feeding into the SSB. We have tried other approaches, so we've also set up a Beaverton-Holt curve, and this was just to try and get around the issue of this period when I think between 1952 and 72, when there wasn't the index, just to try and hold the population growth to the level of B0. And then we've tried bolting on the 3 parameters to the Beaverton-Holt curve as well. But in the end, I think this is kind of the best model we've come up with so far. And here's the fits to the abundance index. So this is coming out pretty well at the moment. It's kind of tracking the middle of the CPUE. And here we have the selectivity curves. So on the right, we see the logistic curve for the long-range fleets. L50 is coming out at about 106 centimeters, which, I mean, I had a look at the previous model, and it seems like be overshooting it a little bit. And here we have the dome-shaped curves for each of the commercial fleets. Bait boat is the furthest to the left, followed by Handline and the Troll, and then further to the right we have the Seine and the other ones. So the selectivity is probably, I think we need to have a think about how to kind of improve the selectivity curves. Maybe try some different selectivity functions, and maybe, because the fishing mortality is coming out very, it's coming out high for the immature stock, and maybe we need to kind of drag the earlier part of the selectivity down for the smaller ones to a certain degree. These are set up length-based though, right? And here are the length distributions, and so these are taken over the whole time period, and we kind of see where some of the problems are coming in here. And it's been very hard to track the spiky length distributions in the data. We're having these little blips earlier, kind of for the younger fish. And if we look at the kind of length distributions by season, then we can see the fits. And I think this has been one of the consistent problems of the modeling exercise for us has been trying to capture these kind of spiky length distributions, because there's not really a clear mode moving through the seasons, so it's quite hard to kind of track cohort strength. It's as good as we've gotten so far, but yeah, there's definitely room for improvement here. So problems we've encountered so far is for the recruitment, we utilize a standard Gadget approach, which was is to take 3 parameters. But I mean, this maybe isn't in this case study, maybe this wasn't the best approach to take, or maybe we need to start thinking about introducing penalties for if the variation in recruitment goes too high, or possibly move to a stock recruitment curve, and start thinking about including year class multipliers. Finally, this is probably the direction which we're going to go with in Gadget 3, and that will be to start modeling recruitment as a random effect using the kind of the facilities provided by TMB. So growth, we think there's still maybe a misspecification in the growth model, so we need to go back and look at this. It's maybe because the Gadget utilizes the maximum L infinity, so it could be kind of leading to negative growth in the larger fish. And also it could be a problem with averaging K over the seasons, potentially move to a length-based K, or try maybe alternative ways to look at growth. And then another problem is the spiky length distributions. And for these, it's just maybe trying alternative selectivity functions and possibly clamping parameters to trying to force the selectivity into the right kind of, the right picture. And the next steps. So we're still working on the single area model. We want to check the growth and selectivity, possibly also try some different likelihood functions. Once we've got to a stage where we're kind of happy with this model, we'll then run a full set of diagnostics, including retrospective analysis, leave one out, and jitter, just to kind of make sure the model's in the right spot. And then we'll start adding the tagging data. So it's interesting from the last presentation about how including tagging data kind of drags up F, which is a kind of something we're anticipating and hoping for, that it will kind of improve some of the model fits. And then we'll kind of run it on the other 100 sets of inputs. And there's also for the recruitment, there's a random effect, something we're keen to try out at some stage using Gadget 3. And then we haven't, as a group, we haven't really discussed the multi-area approach yet. We've just been focusing on the single area model. So that these are really to be discussed in the future. So I guess the takeaway at the moment is it's been a bit of a kind of banging our head against the wall a bit, trying to get the single area model working. But I think that now we're heading in the right direction. Still some tweaks left to do, and but we're hoping to kind of get moving on the multi-area part relatively soon. And the focus of this workshop is the kind of decision point analysis, but we haven't been able to add much to that just at the moment. But hopefully, when writing up the reports or when we meet for the next workshop, either remotely or in person, we'll be able to do that. We'll be able to give you a proper update on that, the kind of decisions we make going with the spatial model. Yeah, so that's it. Thank you.
All right, thanks very much, Will. Yeah, let's maybe keep the presentation. Oh yeah, you got it there. Okay, just in case there's questions on anything specific. Yeah, so we'll open it up for questions for Will and Team Gadget and what they've done so far. Go ahead and raise your hand if you have one. And maybe while people are thinking, I'll just make a comment. It's really interesting, Will, even the decision points that have been made so far in terms of, perhaps sometimes these decisions are based on the software we have available and how much effort it takes to alter that and do the things we want. One of the advantages of Gadget, I see, is it's already ready to implement random effects in recruitment, as you mentioned. So I'm really interested to see, how that turns out when you guys get to it. And I'm also curious about the way in which recruitment is used or estimated in terms of free parameters, and how that's going to perform when moving to a 4-area model, given the additional potential confounding, if as free parameters that makes it even more difficult, maybe compared to a functional form or with recruitment deviates or what have you. So some interesting avenues there. And again, even in a 4-area model, how random effects might improve things relative to free parameters. So, already some very interesting kind of avenues to explore. Yeah, go ahead.
Oh yeah, so I think it's the random effects is quite a kind of an exciting venture for Gadget, and we were working with Jamie over the summer to try and get it up and running. So I think it should be fairly, something we're going to be trying out and trying to get rolling fairly soon. I think this will be a good case study to try and roll it out in. Regarding the free parameters for the multi-area model, I kind of agree that this might become a problem, and I'll probably start looking into kind of stock recruitment curves for parameterizing recruitment. I think one of the benefits of this workshop is actually that we've now we've got some ideas for add-ons to Gadget in terms of the stock recruitment, and so I think this will be a good opportunity to add these in.
Okay, great. I see, Dan, you had your hand up. Go ahead.
Yep. Yeah, so this is kind of an open-ended question, but along the lines of sort of how you analyze the data and some of those decision points and things like that. I know you mentioned you use the MFDB database and to kind of analyze your input data. I was wondering if you could maybe just talk about that a bit and how that influenced some of those decisions just in like the one area model, and if you kind of noticed anything in the data that might influence your how you set up your spatial model and things like that.
Yeah, so the MFDB database is so it's kind of our go-to method for storing the data at MFRI and then kind of using it as a tool, so you can develop tools on top of it to visualize data and then run the kind of to getting it ready for running Gadget. In terms of, in this particular case study, I mean, kind of getting the data into MFDB was what got me familiarized with the data. And so it's kind of how it's set up and how to read it in kind of what structure I wanted to read it into MFDB. I'd have to think about it a bit more, but I'm sure it did inform my decisions as to how I set up the model. I can't tell you off the top of my head what they are.
Okay, well, I see Bjarke has his hand up, maybe from earlier, so maybe, Bjarke, go ahead. Maybe you have a comment from before or anything you have, go ahead.
Well, I can actually comment on the one that you were also talking about, the MFDB. If I remember correctly, that you're trying to put it analyzing the data, you actually notice discrepancies between the 4-area model and a 2-area model, because you can. So MFDB can allow you to import data from various sources. So you can do these spatial analyses. You can mix and sort of merge data sets depending on what attributes you want. So if you want to have area-based, if you want to have an area split in the data, you just specify it in the beginning of the query. And if you don't want to have that, you can merge those into one unit. That's just a simple query, and the rest of the queries all sort of match up. So it allows you to sort of quickly create new data sets based on the same data. So it stores data minimally aggregated, so you can use it going forward into your model, whichever way you want to aggregate them. But I just wanted to comment sort of more about the random effects being the main, going through this journey of trying to build a model that Will has been going through. The main thing has been to sensibly sort of clamp down the range of parameters, and it sort of, yeah, it's one of those things. If you have a fairly if you have a fairly detailed data set, you can put in as many parameters you want. Sort of, you will get a sort of almost sensible estimate. But in this case, you really need to build in a couple of assumptions for the entire thing to work. And so there's quite a lot of there's quite a lot of things you just need to just take at face value from the operating model, which just for this exercise to work. And I think that's a sort of a key thing here. And if you were to approach this problem without knowing anything about the underlying parameters, it's going to be you're going to run into a higher degree of problems.
Yeah, thanks for that, Bjarke. I also think, just to add on to that, the way, and I don't understand it, but the way you've described the MFDB approach, it seems very useful in terms of aggregating data to different spatial hypotheses, if you will. In the simulation experiment, we kind of ask for a 1-area and a 4-area, and you can explore other areas if you want. But operationally, when you're developing assessment models, you're likely going to have to aggregate the data and test a couple different spatial configurations, perhaps even as sensitivity models. I mean, so, and typically those decisions are made at square one, and then you build your data up. So to go back all the way to square one is not feasible. So to have something that can quickly aggregate data to different spatial units and things like that seems really advantageous.
Yes, and I totally agree, and it has been very useful, and not just in terms of the spatial aggregation. It's also just what size distribution you want to work with, or age distribution you want to work with. I think this is a very good. I mean, it allows you to do these analyses quite quickly. So if nothing else, I would totally recommend that you use something similar when you build as a basis for your modeling work.
Dan, go ahead.
Yep. Sorry, my internet is not very good. Yeah, thanks for that. I think that's kind of interesting, how you can disaggregate and aggregate relatively easily. But looking at looking ahead, I don't know that much about Gadget, especially kind of the spatial capabilities of it. And I was just wondering if one of you might be able to give a quick, breakdown or update about what you were thinking in terms of, what the possibilities are for modeling movement, and then this kind of like spatial recruitment, those two processes, and what you were thinking about in terms of handling those.
Yes, I don't know if you want to take this back. So I haven't really used the spatial movement in Gadget much, well, if at all, really.
Okay, so the main structure in Gadget is that you add dimension to your population matrix. So area is simply a new dimension to your work. So it's defining a model in terms of areas doesn't. I mean, it's a fairly simple thing. You just say that you just add a dimension to your stock, and then it can populate different areas. You just attract the numbers of individuals. I think the main trick here is to sensibly parameterize the migration matrix between the areas. And as such, the Gadget framework allows you to set up sort of formulae, so you can specify. First of all, you just specify just proportions that you're going to put in, and these can be estimated. Or if you have some way of thinking about the biomass, you can complicate things as well, because you can set up differences in you can set up functions which could be parameterized in terms of biomass. So you can think about a source sink dynamic or something like that. But from what I gather from the presentation I've seen so far, it seems to be that the populations are fairly the proportions are fairly simple, sort of fixed in the different areas. So you can but then you could sort of parameterize that as just a simple migration matrix. But that's something just we just need to work on and test in the next revision of this model. If that helps answer your question.
Yeah, for sure. That's great. Thank you.
Okay, other questions or comments? I guess I'm going to ask one question if I can. The those examples you just had up there, yeah. Well, yeah, exactly. Are those, is that a two-area COD model, an operational model that's used directly for management, or is that a research model?
It's the exploratory model. That I think it was cod capelin shrimp interactions and the cod migrating north and south. Yeah, it wasn't used for assessments or anything.
Okay, okay, but it would presumably have with migration. It includes a movement matrix, and tracks those, and recruitment in one or more areas, and so yeah, okay. Just was curious. Thanks.
Yeah, it'd definitely be a kind of a jumping off point for figuring out how to, how to parameterize it and everything.
Great. Dan, see your hand up. Go ahead.
Yeah,
sorry,
just
Dan Fu this time. Yes.
Slightly different question. You show some of the feeds to the size data. There appears to be some issues you mentioned about. Apart from those spiky, the issues caused some of the spiky distribution, some of the pool feeds. Do you think how is that related to the fact you use a slightly, I mean, you use a different kind of, you re-parameterize your growth. Basically, the growth is kind of different to what's used in the operation model. I understand we're not trying to kind of replicate what the operating model is doing, but the fact you're using the growth you used, I think you mentioned about how you average across seasons.
Yeah.
I'm just wondering how is that done?
Yeah. So this really came about when I was just doing some patchwork on the model, and basically we have a lookup table for the age and season, which I was using to get the K parameters per pseudo year. But obviously, when we had continual recruitment, this wasn't really an option anymore. So I averaged them, and it was just until I found something like a better solution or something else to test it against. So it's kind of one of the steps I want to do next, and I think the solution will be to just age the stock per quarter, so then these lookup tables will function as we wish them to, and then we can basically carry out a direct comparison between what the effect of averaging K over seasons is, as opposed to taking the pseudo year value at face.
So the growth is still pretty. So the growth is still pretty similar to the original, the each quarterly specific growth. It's kind of similar. I just did the average. That's all I think. Yeah,
I think it's fairly similar, but I mean I can't. So I don't have something to compare it with at the moment. But so we'll be carrying out a comparison of this. I mean, I think we see there's probably kind of a few things going on here. Growth may be part of it. Also the selectivity function that I think we just need to have a little think and test some different ways of implementing these functions to see if this helps iron out these length distributions a bit more.
Will, are the dome-shaped selectivities a double normal formulation or something else?
So it is. Yeah, it is. It's pretty similar. I'm not sure of the exact double normal one, but it's you're going either side of the dome depending on per variant, basically.
It is called an Anderson curve, but it's I think it's pretty much a double normal. It's the I haven't looked at the formulation in stock synthesis, but it's definitely a normal kernel that's used.
Okay, how about last call for questions for now anyways? We will have time again later to revisit. All right, well, I don't see any other hands raised. And I don't see anybody on the phone that may not be able to raise their hand. So I'm going to just assume we're done with questions for now. What we're going to do next is just take a little bit of a break. We've been going for almost 2 hours. So let's take a break until, let's go 55 after the hour. That's just a little bit over 10 minutes. That should give enough people, people enough time to do what they need to do, stretch, etc. And we'll start back up in about 12 minutes. Thanks, everybody. Thanks, Will, for the presentation.
Thanks.
All right, welcome back, everybody. It's 55 past the hour on my watch. And so let's just jump right back into it right where we left off. So what we're going to do is we're going to move on to the third team today. And this is a team working with the software Castle. And they are, as I mentioned earlier, they're going to be talking about applying it to the Antarctic toothfish simulated data. So we've been thinking a lot about yellowfin tuna in the IOTC region. And so you've got to shift your mindset a little bit here. And this is a great segue to also, letting people know that there is a second simulated data set. So there's further opportunities to test out your spatial models. Hopefully it's a little bit smoother given you'll already have a framework constructed with the yellowfin. But at any rate, this is a great opportunity to learn a little bit more about this simulated data set, as well as what the team has been up to. So in way of an introduction, I'd like to introduce Arnaud Gruss. Arnaud is a fisheries population modeler at NIWA, the National Institute of Water and Atmospheric Research in Wellington, New Zealand. He works with different models that have spatial capabilities, including models such as VAST, the Vector Autoaggressive Spatiotemporal Model, and SPM, the Spatial Population Model. He is leading the Ross Sea Region Antarctic Toothfish Stock Assessment. And NIWA has a long-standing, or has long been using Castle for the Ross Sea Region Antarctic Toothfish Assessment. And that's what he'll be presenting on. And their plan is to, in the future, transition that to Castle 2 in 2023. To be technically correct, I think I've been saying that the team is going to use Castle 2 today. Just want to just be clear that they're using Castle, and the nuances and improvements that Castle 2 will have. Sounds like they will be available in 2023. Anyways, Arnaud can tell us more about that if needed. So yeah, looks like you're already sharing. Perfect. Go right ahead, Arnaud, and take it away.
Yeah, thank you very much, Aaron. So very nice introduction. So that will shorten my introduction quite a lot. Yeah, and thanks a lot, everyone, for attending this presentation today. So my name is Arnaud Gruss from NIWA Wellington. So I'm presenting the spatial simulation experiment for Ross Sea Region Antarctic toothfish today on behalf of our NIWA team. So as Aaron said, that's a work we've been doing with a Castle modeling platform, which is a modeling platform developed in New Zealand that we use a lot for our stock assessments. And as Aaron said, so we've started to transition to Castle 2, but for the stock assessment of Ross Sea Region Antarctic toothfish. But in effect, we are going really to conduct the actual assessment with Castle 2 only next year in 2023. So today, there will be 6 different parts in my presentation. So I will start with a few slides just to present Ross Sea Region Antarctic toothfish, because as Aaron said, that's a case study that I'm the only one to have picked. And so a lot of people are not aware about this fish stock. And it's actually an interesting case study because it contrasts with yellowfin tuna, because in the case of yellowfin tuna, we have a population that understands that undertakes these massive seasonal migrations, and that's an important ecological feature to consider to structure the spatial stock assessment models. But in the case of Antarctic toothfish, so the key ecological feature to consider are the ontogenetic migrations that toothfish undertake, where the toothfish move into deeper waters, so more and more into deeper waters as they grow older. So yeah, the first part of this presentation will be about Antarctic toothfish in the Ross Sea, and then I will say a few words about the operating model that was developed for Antarctic toothfish for this spatial assessment modeling workshop. So that's an operating model that relies on the spatial population model, which is also a tool that has been developed at NIWA. Originally actually for Ross Sea region Antarctic toothfish. Then I'll be describing the stock assessment models that we've been developing for the spatial assessment modeling workshop, so the 1 area and 4 area models. And then I'll present the results of workshop objective 1, so where we consider only 1 replicate from the operating model. And after this is done, so I present the results for workshop objective 2, where we consider all of the 100 replicates from the operating model. And finally, so there will be some concluding remarks and some recommendations in terms of potential avenues for future research. So regarding Ross Sea region Antarctic toothfish, so Antarctic toothfish is an economically important large-bodied species that is found in Antarctic and subantarctic waters. So we have 2 species of toothfish in Antarctica. Patagonian toothfish that is found more in subantarctic waters, and Antarctic toothfish that is close to the Antarctic continent. And so, as I mentioned earlier, so really the key ecological feature for Antarctic toothfish are the ontogenetic spatial distribution patterns of this species. So in the Ross Sea region, we find the juveniles and the young adults on the shelf of the Ross Sea region. So that's where they recruit at depths less than 800 meters. And then as they grow older, so the toothfish move progressively into deeper water. And so as a result, we find the oldest and largest Antarctic toothfish in the north, well, primarily in the north of the Ross Sea region. Regarding other ecological features, so spawning in Antarctic toothfish takes place in the north on seamounts, ridges, and banks. And spawning takes place in the winter season. Very likely between mid-July and August. And so that's a fact that is important to keep in mind, because so spawning takes place in winter, but actually fishing in the Ross Sea region takes place only in summer, so during the summer season. And so after spawning, the eggs and larvae of Antarctic toothfish are transported by the Ross Sea gear to the shelf of the Ross Sea region. So we have a life cycle for toothfish that is described on this little figure that is provided on this slide. And we assume that Antarctic toothfish in the Ross Sea region is an enclosed unit stock centered on the Ross Sea gear. And this assumption that we make that is important for the assessment is actually backed up by a number of stock structure analysis. So regarding fishing, so Antarctic toothfish is currently targeted by only one fishery, which is the bottom longline fishery.
that has started operating in the Rossi region in 1997, 1998. And as just mentioned earlier, so bottom long line fishing takes place only in summer in the Rossi region. So fishing starts on the 1st of December each year in the north, and then fishing progresses south as sea ice retreats. And yeah, the fishery then is closed when the catch limit is reached, and this is actually typically in January or February. So as you can see, we have like a pretty short fishing season for Antarctic toothfish in the Rossi region. So regarding, the management in the Rossi region, so a very important event to be aware of is the fact that in the 2018 fishing season, the largest marine protected area of the world was established in the Rossi region. So that's the Rossi region marine protected area. And the establishment of this large-scale MPA has had like massive consequences for management in the Rossi region, because this has led us to totally redefine management areas in the Rossi region, and so also for the assessment of Rossi region Antarctic toothfish. So now in the Rossi region, because of the establishment of the Rossi MPA, we have different types of management areas. With the management areas on this slide that are in red, which are the management areas that are part of the Rossi marine protected area. So first we have general protection zones within the Rossi MPA, where fishing is not allowed. So fishing is totally not permitted. And also within the Rossi marine protected area, we have the special research zone, which is a smaller zone where fishing is permitted, but at a low exploitation rate. Otherwise, the other management areas in the Rossi region that matters for Antarctic toothfish are the S70, so south of 70 degrees south management area, and the north of 70 degrees south and 70 management area. So, and those are two management areas within the Rossi region where fishing is fully permitted. And we distinguish between those two areas because we don't have the same life stages of Antarctic toothfish inhabiting those two areas. So we have predominantly smaller and younger Antarctic toothfish in the S70 management area, and predominantly larger and older Antarctic toothfish within the N70 management area. So now regarding the operating model that we use for Antarctic toothfish for this spatial assessment modeling workshop. So this operating model uses a spatial population model software, so the SPM software. And as I mentioned earlier, the SPM was actually originally developed for Rossi region Antarctic toothfish. And it's only very recently that it's been applied to other fish stocks. So it's been applied, as you're all aware, to Indian Ocean yellowfin tuna, but also recently the SPM has been applied to some invertebrate species from the Chatham Rise in New Zealand. So the latest published version of the SPM for Rossi Antarctic toothfish dates back from 2014. So for the spatial assessment modeling workshop, workshops. So Sophie Mormed has updated the spatial population model for Antarctic toothfish to 2021. And so it's really, so this operating model that we are considering for the spatial assessment modeling workshop is really not for management purposes, but solely for modeling exercises. So that's yeah, a specially explicit operating model where the Rossi region is considered as being made of a number of grid cells, and there are population dynamics happening between these grid cells and also movement between these grid cells. And so for the spatial assessment modeling workshop, a specific management area was assigned to each of the grid cells of the spatial population model. Although, yeah, it's a simplification because in reality, those grid cells very likely, well, in reality, very often fall within several management areas. So again, it's really an operating model for modeling exercises only. So that operating model for the spatial assessment modeling workshop provided us with spatially explicit data. So there were quite a lot of spatially explicit data that the operating model provided, but ultimately we didn't use all of those data in the stock assessment models that we developed for the workshop. So for the different objectives of the workshop, we use so just some of the data provided by the operating model, which include the total catches in biomass for each year of the period 1998 to 2021. We also use the proportions at age of the catch, so provided by the operating model for project for each year of the period 2002-2020. And we use also the spatially explicit tagging data provided by the operating model. So we use proportions at age of tagged and released fish for each year of the period 2001 to 2020, and the proportions at age of fish recapture with a tag for each year of the period 2002 to 2020. So we didn't use the catches per unit effort, CPUEs, provided by the operating model. And the reason why we did this is because the CPUEs are actually not used in the actual Rossi region Antarctic toothfish assessments. Because there's like this belief in our New Zealand fishing group that the changes in Antarctic toothfish CPUE are not consistent with the likely fish down changes in toothfish abundance, and they appear to partially reflect spatial management boundary changes, ice-driven availability, and yeah, on an annual basis, and also the continued improvement in skill and fishing strategy by the fishing fleets. So all these rather than the underlying toothfish abundance. So we didn't use the CPUEs provided by the SPM, and also for our project for the workshop, we didn't use the proportion spawning for each length in the catch that are provided by the operating model, because these particular data also are not used in the actual Rossi region Antarctic toothfish assessment. So regarding the stock assessment models that we developed for the workshop, so those are implemented using the Castle software package, which is a standard assessment modeling platform in New Zealand that we use for quite a lot of assessments here in New Zealand, and which shows Castle for the workshop, because Castle has special capabilities. So with Castle, it's possible to implement areas as fleets models. And so that's what we did for the workshop. But also with Castle, it's possible to implement spatially explicit models with migrations that are being simulated between the different regions considered in the spatially explicit model. And also it's interesting to note that in New Zealand, most of our spatially explicit stock assessment assumes natural fidelity. So with Castle in New Zealand, we are able to account for the fact that fish that are spawned from a given stock will return to their natal spawning ground. Also, besides the fact that Castle has special capabilities, so which shows Castle because Castle can account for tag releases and recaptures by edge and length. And this is very important to conduct an assessment of species like Antarctic toothfish, for which we have like a lot of tagging data. Examples of spatial stock assessment models with Castle include the actual Ross Sea region Antarctic toothfish assessments, which relies on areas as fleets model, where tagging data are critical data inputs. Another example of areas as fleets model with Castle is the one that is implemented in New Zealand for our Kauai stocks. Also, Castle is used in New Zealand for snapper assessments, and in that case, so for the assessment of snapper for the northeast coast of the North Island, we use a spatially explicit Castle model with 3 regions, 3 stocks, and natural fidelity with periods of mixing. And also, Castle is used for an economically important stock here in New Zealand, Oki, and in that case, Castle is used as a spatially explicit assessment model with 4 regions, 2 separate spawning stocks, and natural fidelity with separate stock spawning grounds. So for the workshop, we developed 2 types of assessment models. So we developed 1 area models and 4 area models. And our 4 area models were areas as fleets model. So that means that those 4 area models accounted for some spatial structure by estimating separate fishing selectivities for the 4 different management areas of the Ross Sea region, which are the General Protection Zone, the Special Research Zone, the S70 area, and the N70 area. So for the workshop, we developed unsexed Castle models, but actually the actual Ross Sea region Antarctic toothfish assessment model is a sexed model. And so we developed unsexed model for the workshop because the operating model did not provide us with sexed data, but rather with unsexed data. Also, our Castle assessment models were edge structure models, where we represented the dynamics of toothfish aged between 2-year-old and 30+-year-old. And so the reason why we represented those particular edge classes is because the operating model provided us with data for those specific edge classes. And so with the Castle assessment model that we developed, we followed tag cohorts through time. So more precisely, we followed 20 tag cohorts that corresponded to the tag releases that happened in years 2001 to 2020. So with the castle assessment models that we developed, we represented tooth-speech dynamics in years 1995 to 2001. So we started running the model just 2 years before phishing started operating in the Rossi region, and 2021 is our current year. So that's the last year for which we had data provided by the operating model. And so based on the ecological features of Antarctic toothfish in the Rossi region that I mentioned earlier, so we chose to divide all castle assessment models for Antarctic toothfish. I mean, the year we chose to divide each year in those assessment models into 3 time steps. And those 3 time steps included summer, so November to April, winter, which is May to October, and the very last time step was a simple edge incrementation time step. And so, as I mentioned, as I just said, we divided each year into 3 time steps based on the ecological features of Antarctic toothfish in the Rossi region, and also based on the characteristics of the bottom longline fishery in the Rossi region. And so in our assessment models, in time step 1, recruitment takes place, and then we simulate the tag release and tag recapture processes. Next, still in time step 1, we apply half of the natural mortality. And then after that, still in time step 1, we apply instantaneous fishing mortality. And then in time step 2, so we start by applying the second half of natural mortality, and we simulate the spawning process. And so the spawning stock biomass, SSB, is recorded after half of the natural mortality has been applied in time step 2. So all castle models for the workshop include 2 types of models. So first, we developed 1 area models where we consider only 1 single fleet, which is a Rossi region fleet. And then what we did is that we developed 4 area models, so 4 areas as fleets models, where we considered 4 fleets, so where each of these fishing fleets corresponds to a particular management area in the Rossi region. So in the 4 area models, we have an N70 fleet, an S70 fleet, a special research zone fleet or SRZ fleet, and a general protection zones fleet, so GPZ fleets. And so for each of the fleets represented in our castle assessment models, so we estimated selectivity at age, and we assume that selectivity at age followed a capped double normal distribution. And we estimated the parameters of the selectivity at age functions. And so what we did is that in the 1 area model, so the selectivity at edge parameters in the 1 area model were estimated using the same priors as the priors for the main fleet in the 4 area model, which is S70 fleets, because so in the Rossi region, the great majority of fishing takes place each year of our study period within the S70 area. So we provide annual catches as inputs to the castle assessment models. And in Castle, we assume a maximum fishing pressure of 0.999. And to impose constraints in our assessment models, we implement catch limit penalties and also some fish tagged penalties. Proportions at edge are provided to Castle as observations, and along with those proportions at edge, we provide input sample sizes for the different years for which we have proportions at edge. And so here we're using a multinomial distribution, and what's important to note is that we provide input sample sizes to the Castle assessment models, but those input sample sizes are reweighted using the Francis method because we want to downweight the influence of proportions at age compared to the influence of tagging data in our Castle assessment models, since the annual trends in Castle will be informed by the tagging data, as we are not providing CPUs, and we want tagging data to have more influence in the assessment models than the proportion at age data. Regarding tag releases and tag recaptures, so for each year of the period 2001 to 2020, we specify a total number of tag releases and proportions tag at age in Castle. So those are provided as inputs of the Castle assessment models. And also we provide tag recapture observations to the Castle assessment models. So for each year of the period 2002 to 2020. So we provide the Castle assessment models with proportions scanned at age and proportions recaptured at age. And so what we do is that we ignore the in-year recaptures, and we consider only the tags that have been at liberty for a maximum of 6 years, as this is something that we also do in the actual Ross Sea region Antarctic toothfish assessment. So we use a quasi-binomial distribution for the tag recapture data, and so this means that we have a dispersion term for the tag recapture likelihood. And this dispersion term is initially set to 1, but it is then reweighted using a procedure from Francis, and this so as to again give more importance to the tagging data in Castle compared to the proportions at age data. So regarding the recruitment process in our assessment models, so we assume that fish recruit at age 2 based on the guidelines that were provided to workshop participants. And we model the recruitment process using Beaverton-Old spawning stock recruitment relationship, where recruitment is given by the unfished recruitment R0. And we use a steepness parameter of 0.75 based on the guidelines that were provided to workshop participants. And with the Castle assessment models, we estimate your class strengths in each year of the period 1993 to 2009. And we estimate your class strengths YCS for those particular years since fish recruit at age 2 in the assessment models. Regarding the maturation process, so this process takes place in step 2, and we specify maturation as a time invariant proportion of fish at age that are mature, and we use a logistic function and the parameters coming from a seminal paper on Ross Sea region Antarctic toothfish. Otherwise, we use the natural mortality and growth length weight parameters that were provided to workshop participants. So now I'm going to report the results that we got for workshop objective 1. So in workshop objective 1, we consider only one of the replicates from the operating model. And so to address objective 1, we use replicate 2. And what we do with observations provided by replicate 2 is that we developed 1 area and 4 area castle models, and both of these castle models were run in the maximum posterior density mode, so in the MPD mode, and in the Markov chain Monte Carlo MCMC mode. And so running those castle models in the MCMC modes allowed us to have like estimation of uncertainties around parameter estimates and derived quantities. And so to evaluate the 1 area and 4 area castle models, so we developed quite a lot of diagnostics that are provided in the extra slides at the bottom of this presentation. So the presentation will be made to you guys, so you can just examine them. But so just very briefly, we developed a whole bunch of diagnostics. So looking at things like the Pearson residuals of the proportions at age, bubble plots of the Pearson age residuals, and we looked also at the Pearson tag recapture residuals, and yeah, a bunch of other diagnostics for the age and tagging data that are listed here. And since for objective 1, we also run castle in the MCMC mode, so we looked at MCMC posterior trace plots and at a number of classical MCMC diagnostics. And also we looked at MCMC predicted median ages versus observed median ages in the catch for the different fleets represented in the 1 area and 4 area castle models. So first, here I'm showing you guys a few results that we got that are relative to biomass, spawning stock biomasses and recruitment. So with the castle models run in the MPD and MCMC modes, we look at the results in terms of spawning stock biomass, initial SSB B0, initial recruitment R0, and current stock status. Well, current SSB, so biomass in 2021, and current stock status, which is given by the ratio of the biomass in 2021 over initial biomass. And so what we observed when we compared the results of the 4 area and 1 area models is that all of the spawning stock biomass quantities and R0 were all slightly higher for the 4 area model than for the 1 area model. So that's what you can observe here with those figures provided here and the numbers that are reported in the table provided in this slide. So also what was interested is that since we run the castle assessment models in the MCMC mode, we were able to to look both at mean expected quantities, but also at uncertainties around derived quantities. And so what we were able to observe by looking at the MCMC results is that B0, R0, biomass in 2021 and current stock status were all slightly higher for the 4 area model, but also all of those quantities were also less uncertain for the 4-area model than for the 1-area model. Also, if we look at the results in terms of current stock status, we could actually interpret that the 4-area and 1-area models estimated a relatively similar current stock status. So next we look at the results from the assessment models relative to fishing pressures. And what we observed when we looked at MPD and MCMC results is that the 4-area model usually estimated slightly higher annual fishing pressures than the 1-area model. Next, we look at the results in terms of catch. And so we look so at the total catch in the 4-area model for the 4 different fleets that are represented in that 4-area model. And we look at the total catch in the 1-area model, so which is for the Ross Sea region fleet. And what we observed is that the trends in total catch for the Ross Sea region fleet in the 1-area model are similar to the trends in total catch for the S70 fleet, which is the main fleet in the 4-area model. And so for both the Ross Sea region fleet in the 1-area model and the S70 fleet, we observed an increase between 1997 and 2021 in total catch that reflected the tendency for fishing effort to be more and more concentrated on the slope of the Ross Sea region since the start of the bottom longline fishery in the Ross Sea region. Also, what we observed by looking at the results in terms of total catch is that in recent years, there was a slight increase in the total catch for the N70 fleets that mirrored the decrease in total catch for the GPZ and SRZ fleets. And so this slight increase in total catch in the S70 fleet is most likely due to a displacement of fishing efforts from some displacement of fishing effort from the Ross Sea Marine Protected Area to the north of the Ross Sea region since the establishment of the Ross Sea region MPA in 2008. Next, we look at the results in terms of selectivities at age. And so what we found out is that the estimated selectivity function for the Ross Sea region fleet was similar to the estimated selectivity function for the S70 fleet. So again, the main fleet in the 4-area model. So for both the Ross Sea region fleet in the 1-area model and the S70 fleet, we obtained dome-shaped selectivity at age. And that was also, we also got a dome-shaped selectivity at age function for the SRZ and GPZ fleets. And the estimated selectivity function for the N70 fleet is different. So for the N70 fleet, the 4-area castle assessment model estimated flat-topped selectivity at age. And this reflects the fact that the oldest Antarctic toothfish in the Ross Sea region are found in the north of the Ross Sea, and those are fully selected so by the N70 fleet. So next, we looked at the results in terms of abundance at age, and so when we looked at the MPD results, we noted differences in abundance at age between the 4-area and the 4-area models. In particular, more variability in age structure for the younger toothfish in the 4-area model. And this was even more the case when we looked at the abundance at age predicted by the assessment model in the more recent years. But also we looked at the MCMC results, and when we looked at the MCMC results, is that what we noted is that there was more variability in edge structure for the younger toothfish in the 4-area model than in the 1-area model, but also more uncertainty in the estimated edge structure in the 1-area model. So finally, we looked at the results in terms of your class strengths, and what we found out when looking at the results in terms of your class strength is that the results explain the differences in edge structure we had noticed earlier, because the estimated your class strengths had more interannual variability, but were also less uncertain for the 4-area model compared to the 1-area model. So next, in terms of results for Objective 2, so for workshop Objective 2, we looked at the results across the 100 replicates predicted by the operating model, but this time we ran the castle assessment models, so the 1-area and 4-area models only in the MPD mode, because MCMC runs takes really a lot of time, so it was not doable to run MCMCs for workshop Objective 2. And again, so as we did for workshop Objective 1, for workshop Objective 2, we compared the results of the 1-area and 4-area models. So in terms of spawning stock biomasses, fishing pressure, edge structure, and your class strengths. And in addition to that, compared to workshop Objective 1, we also produce box plots of B0, biomass in 2021, current stock status, and R0. And we compared those box plots for the 1-area and 4-area model. And also, because the operating model provided us with a value for R0, but R0 is estimated by the 4-area and 1-area model, we were able, because of this, to estimate bias in the R0 that is estimated by the 1-area and 4-area models, and compare biases in R0 for the 1-area versus the 4-area model. So regarding spawning stock biomasses, with 100 replicates, once again, we found that the spawning stock biomasses were higher for the 4-area model than for the 1-area model. And regarding the median fishing pressures over the 100 replicates, what we observed is that those median fishing pressures over the 100 replicates tended to be very slightly higher for the 4-area model than for the 1-area model. Regarding abundance at age, estimated by the castle assessment models. So again, we noticed with the 100 replicates differences in the abundance at age estimated by the 4-area and 1-area models, especially more variability in edge structure for the younger toothfish that are younger than 15-year-old in the 4-area model compared to the 1-area model. And again, the results in terms of edge structure could be explained by looking at the results in terms of your class strengths. So when we looked at the individual replicates provided by the operating model, again, what we noticed is that the estimated your class strengths had more interannual variability for the 4-area models than for the 1-area model. And so you have like a couple of examples that are provided on this slide. So we looked also, so we also produced box plots of B0, current biomass in year 2021 and current stock status. And looking at these plots, we saw that the initial spawning stock biomass, so B0, was higher for the 4 area models than for the 1 area model. We also observed that biomass in year 2021 was very slightly higher for the 4 area models than for the 1 area model. And finally, we found that current status was similar for the 4 area and the 1 area models. Regarding the results for initial recruitment B0, so we found that the estimated initial recruitment was higher for the 4 area models than for the 1 area model. And so, as I mentioned earlier, because the operating model provided us with a value for B0, for R0, sorry, while R0 is estimated with the castle assessment model, we were able to evaluate bias in R0 for the 1 area and the 4 area models. And so it's interesting to evaluate bias in R0 because in areas as fleets assessment models, we are making the important assumption that the probability of recapturing a tagged fish is the same as that of an untagged fish. And this irrespective of the location at which tagged fish were released or the subsequent spatial distribution of fishing effort from which fish are scanned to detect recaptures. So in other words, in areas as fleet models, we are assuming complete mixing of tagged and untagged fish. And this is a very strong assumption that is likely not met in the real world because of the spatial management that we have in place in the Rossi region, but also because of the constraints imposed by sea ice extent on fishing. So imposed on the spatial distribution of fishing vessels, and also Rossi region Antarctic fish actually move over relatively short distances. So for all of these reasons, it's very likely that our strong assumption of complete mixing of tagged and untagged fish is not met in the real world. So we looked at the bias in R0, and we found that R0 was biased low by more than 40% in both the 1 area and 4 area models. However, the negative bias in R0 was found to be significantly lower for the 4 area models than for the 1 area model. So in conclusions, compared to the 1 fleets as areas model, so the 4 fleets as areas model predicted slightly higher spawning stock biomasses, B0, current biomass, and annual fishing pressures, but predicted similar current stock status. Also, the 4 area model allowed for the estimation of several selectivity at edge functions that accounted for the ontogenetic migration patterns in Rossi region Antarctic toothfish. And the 4 area model was able to estimate year class strengths that had more interannual variability and were also less uncertain. As a result of this, the 4 area model predicted more variability in the edge structure for the younger toothfish, and also the edge structure predicted for toothfish was less uncertain with the 4 area model. Also implemented a 4 area model instead of 1 area model resulted in slightly reduced bias and error in the estimated R0. So finally, I'm going to conclude this presentation with a few avenues for future research. So possibly future studies could try to apply, well, use Castle2, use a Castle2 model with the data that were simulated for Rossy region Antarctic toothfish for the workshop. And what would be interesting then would be for this Castle2 model to be spatially explicit and to represent migrations between different regions of the Rossy region. Also, potential avenue for future research would be to improve the current spatial population model for Antarctic toothfish and later estimate biases in stock size for Antarctic toothfish to inform management within the camellar space. And regarding the improvements that would be introduced in the operating model, what would be particularly valuable would be to represent the Rossy shelf survey in the operating model. And this way, we could have catch-at age data for young toothfish, and this would allow us to better than estimate year class strengths within the stock assessment model fitted to data simulated by the operating model. And so finally, I added one final thought that came from Simon about the tagging data, and it's more something I'm not really familiar with, and it's more like something that I included in this slides just as food for thought later in the process for this workshop. So yeah, thank you very much for your attention. Sorry, I've talked quite a lot, a bit more than I was supposed to.
Well, thanks very much, Arnaud. And I think it was, I appreciate anyways the depth that you went into, given that many of us haven't really thought about this data set too much yet. So that was really helpful to kind of set the stage. So thanks very much. Yeah, great presentation. Let's open it up to questions. Simon, looks like you were first. Go ahead.
Yeah, thanks, and thanks, Arnaud. I had an initial question about something that is relevant to this presentation, but also to the yellowfin presentations, which is about the that sort of mixing latency period issue. Given that as you mentioned, you have this bias in biomass that's driven by the tagging data due to the lack of mixing. And that's an issue that comes up with tuna assessments as well. In the yellowfin assessments, they have this latency period where they allow a period for mixing. And in this assessment, what happens if you extend that latency period? I think you don't include recoveries in the current year, but you include recoveries in every subsequent year, up to 6 years. If you extended that mixing latency period, would you get less bias? I mean, I guess it's obvious because you'll have less tagging data in the likelihood then, so it will be probably causing less bias. But I just wondered if you'd like to talk about that one. Thanks.
So when do you talk about the latency period? Are you talking about the time at liberty, which currently we restrict to 6 years in our assessment models?
Yeah, I'm not sure if it's available in Castle, but in say stock synthesis or multi-fan CL, there's a parameter which is the mixing period, and rather it's the delay before tags start to be included in the models. So if you release them in year 1 and there's a latency period of 2 years, they wouldn't be included in year 2, they wouldn't be included in year 3, but they would be included in year 4, or maybe not in year 1, not in year 2, but they would be included in year 3. So there's that latency period is a delay, and then after the delay, they're included in the likelihood. So that gives the tags sort of a couple of years to mix through the population and until you get the same proportion until you assume that the tags are completely mixed. So any sample will have the same proportion of tags in the recoveries as are in the population.
Okay, I see. Well, probably it's pretty straightforward to implement then, because you just choose to drop, for when you consider the tag recaptures, you consider tag recaptures relative to the years of tag releases. And so to implement what you describe, probably what we would need to do would be to drop the first few years of tag releases. Just consider just like, the years, something like 3 or 4 years after the tagging was done. But yeah, obviously, if we do this, it means it's a very important, since tags, we don't use CPUs. Tags are driving the assessment, so those are the main data sources in the assessment that are driving pretty much everything. If we just try this kind of changes, it would be this would be very important sensitivity analysis that probably we would have to present several times to Camela before they are convinced that that's something we could do for the actual assessment.
Thanks, Arnaud. Yeah, it seems like there's always a trade-off of delaying the mixing period, because effectively you're throwing that information out because it invalidates assumptions, but then also reducing what you have for data that comes from the tags. So it's an interesting concept to continually think about. But I did see, Jeremy, you had your hand up. Maybe a new comment or things to add here.
Yeah,
go ahead.
So, thanks, Aaron. I've been through this with Arnaud before, and I just sort of just wanted to clarify something. Arnaud, this is a really interesting result because it's showing the problem of incomplete mixing. The fact that you've got spatial heterogeneity in the tags, but the fact that in some areas you're tagging adult fish, in some areas you're tagging juvenile fish. And then through time, these fish move around as they age. So the interesting question is what period of latency that Simon raised would sort of mediate that initial bias. The model's going to assume that it's all homogeneously mixed from the start. If you say you're not going to look at them till they've been out for 6 years, then maybe that homogeneity assumption is met. But it's interesting to test that. And I just have a question on the tagging data, because it is actually driving your whole abundance in your model. I'm assuming you are kind of using it as a relative change in abundance, because you explicitly not, I mean, the model will sort of interpret into particular ways, but are you telling it about like initial mortality, tag loss, those sort of things that affect the absolute interpretation of the mark rates? I mean, how is your model dealing with the uncertainties around whether you're actually seeing all the tags and all the tags are surviving?
Yes, indeed, you consider those data as relative, providing relative information, and then you also specify a number of things about the tagging process. So tag loss rates, what is called shading. You also assume like a mortality specifically for the tagged fish. Yeah, and you don't assume the same rates for fish that have been single tagged and double tagged as well.
So the model is pretty much interpreting the tags as an absolute signal. Marked unmarked ratio kind of. So it's going to interpret a mark rate as a binary.
Well, actually, yeah, it's more absolute because there's no scaling that is being, estimated by the assessment model. So that's correct. Yeah.
So you are adjusting for that, but that sort of uncertainty is going to propagate in there as well. So scanner success, reporting success, tag loss, whether they're doubled or single tagged. Those factors are in your model, but uncertainty around them will affect the assessment as well.
Yeah, that's right, because we provide just one single value for those. But I think there have been pretty sure there have been like sensitivity analysis done early on, when toothfish assessments were initiated, just to evaluate the consequences of alternative values for those parameters. And I think just the current deterministic values that we use are just like based on those past analysis.
So in the operating model, those were sort of fixed. I mean, those features were in the operating model and it generated data, presumably.
So no, so what we are discussing right now in terms of tag loss, tag shedding and everything, that's in the actual assessment. The operating model didn't provide any of those quantities. And for that particular reason, I didn't represent, tag mortality, tag shedding, and so on in the assessment model specifically developed for the workshop.
Okay, so you ignored those factors because we weren't provided with them in your assessment, in your simulation assessment.
Yeah, but even if I ignore them just for the workshop modeling exercises, I think it's very great that you raise these issues, because that's how, those are extremely important issues in our real world spatial stock assessments. So that's an opportunity just to raise those issues.
I think the fundamental one is the point that you've shown is that in the operating model, there was spatial heterogeneity in the way the tags went out, because at certain areas you were tagging certain proportions of the population, and in your estimated models, you were kind of ignoring that. And the implicit assumption was homogeneity of recoveries, and it showed pretty dramatically that when that assumption is not strongly met, you can get, in your case, a 50% underestimation of productivity.
Yeah. And as a result as well, number of parameters, I guess, well, that's what the workshop participants can see, in the extra slides. So the diagnostics were good overall, but there were a bunch of parameters like selectivity at age, for instance, where, the MCMC results were not that good. And I think it's largely because of like this, tag mixing assumption.
Yeah, thank you. And it's one of the things that was a difficult component of creating the operating models and deciding, what to provide you all with in terms of known things. Because obviously, if you start with a blank slate, you can very easily become, from an experimental standpoint, not very tractable. And so that was one of the points that we discussed quite a bit on what to provide as inputs, so that you know, we could keep the experiment a little bit on track. But nonetheless, that's a really good point that, you know, spatial tagging data in general has a bunch of assumptions associated with it, right? And not just recapture, but you know, tag related mortality, recovery rates, differences in those by fleets, for example, in the elephant model, et cetera. And so those are things that underpin a lot of what we're doing here, but are certainly important. Let me move to, I see Dan has his hand up. Let's go. Yeah, go ahead, Dan.
Yep. So I had two kind of related questions. The first one was along the lines of what kind of led you guys to choose the fleets as areas model over a more fully spatially explicit? Was there anything in the data, or, you know, like some data analysis that kind of led you down that reasoning and rationale? And then the related one was, do you think that given the kind of complex fishery dynamics, mostly those, you know, basically closed areas to fishing, do you think that kind of do you think the dome-shaped selectivity in a fleets as areas is adequate to deal with that kind of complexity? And might that also be something that, you know, having tagged fish move into closed areas and not being susceptible to fishing, you know, might that be part of the problem, not just tag mixing itself? Sorry, it's a long, complicated question.
I know it's pretty clear, Dan. Thank you. Well, we chose the fleets as areas because I think when you want to develop a spatial assessment model, you will start with this kind of model that is more simple than a spatially explicit model with movement between regions. And that seemed to be like a very good choice to deal with a, you know, with a fish stock that undertakes these ontogenetic migrations, where the fleets will be related to the management areas, but also to the ontogenetic spatial distributions. And so we would account with the fleets, and therefore with the selectivity that edge functions that are estimated for different fleets, we could just account for those ontogenetic you know, habitat shifts in the assessment models. Now, in terms of whether we will do a better job with different selectivity at edge functions and just moving away from fleets as areas, well, clearly for the N70 fleet, you know, we get a flat top shape that I think more accurately reflects how fishing select individuals there, you know, based on fish that are found there. But with a dome shape area, with the dome shape like selectivity functions that we get for the other fleets, yeah, I'm not entirely sure, because, you know, clearly you don't want to select like the oldest, the largest and oldest fish, but some of those fleets probably targets more of the young as individuals as is currently estimated by the models. So I guess I would be like curious to hear any suggestions, like any alternatives you would have in mind to the dome shape function.
I don't have any suggestions personally. But yeah, I mean, that all makes sense to me, especially starting simpler and working your way to more complex.
And I think that's a part also of the software platform, because Castle has become quite old, and we've had like a lot of issues, computational issue, even, you know, with fleets as areas models. And we had concerns that moving to spatially explicit assessment models, just like the model will crash, because that would be too much for Castle. So I think it will be, implementing a spatially explicit assessment model will be for Ross Sea region Antarctic toothfish will be much more doable with Castle 2.
Thanks, Arnaud. I do want to note that we've moved into the discussion period, so I want to open it up. Rick, I see your hand. We'll get to you in just a second, but I do want to make sure we open it up. And if there's any questions for any of our teams that presented today, those we're moving to that period, so we can do that. But let's, Rick, you got your hands up, and maybe it's on the toothfish presentation. Go ahead.
Well, it certainly leverages off of that presentation. There was just discussion about starting simpler and then moving to more complex. I think the caution, and it's a mistake that I've seen made, so I just want to put the caution on the table. If you start with a simpler model, you need to start with simpler data too. You can't give a simple model data that could only be fit if you have a complex model. So because the complexities of this additional data may have features that you need to invoke the more complex features that are in the complete model. So scaling back the data so that you really are looking at a simple situation with only simple data, I think that is a very important thing to do, but scaling up data in concert with the model is what I think we don't have good protocols for doing that.
Yes, thanks, Rick. Good segue to all the models we've been discussing, really. Okay, opening it up to a general discussion, observations or comments, similarities, differences that you see, anything. Feel free to raise your hand.
This is Dan again. I mean, just adding to Rick's comment, I mean, I think that really ties into what the Gadget group presented there with being able to scale from aggregated to disaggregated to aggregated, and having different aggregation levels, and like having that ability to move easily and flexibly between aggregations spatially, temporally, things like that. Like those kind of data tools might be the most complex and most important part of actually developing kind of these spatial models. Is you really need to analyze the data disaggregated and then have that ability to move to different resolutions flexibly and easily, I think.
Yeah, I would tend to agree with you on that. In general, I think this is a recurrent theme to many workshops that we've seen. I can think of an ecosystem modeling workshop that ICES is trying to work towards, where the simulation model is Atlantis, and they are trying you're testing quite a lot of different modeling frameworks, and then at the crux of that problem is the work towards aggregating data, and that's sort of one of the key issues that we have to deal with. I think they are dealing with, and I can probably not mention a couple of other sort of instances where you will run into this problem of how do you aggregate data and how you work with them is in a sort of transparent and reproducible ways. It's definitely worthwhile having the right tools for that.
Okay, other questions or comments? All right, well, perhaps people are thinking. I'm going to just ask one. It's a little bit more technical, so I wanted to just preface it by that a little bit. I was curious, and this is for the toothfish example, Arnaud. So I understood that you guys used MCMC And I just was curious on your, and you mentioned some constraints in terms of time to run those MCMCs. And while there's, methods now to significantly decrease that time, as we move to spatial models or in spatial modeling cases, that's going to increase time. So we might, counteract those technological increases. So I was just curious if you had any thoughts on some of the insights that you might have gained by conducting your assessment in an MCMC framework. And maybe in particular, I guess where I'm coming from is I was very curious to see the variability within a single replicate via MCMC, which better captures uncertainty, of course, or in theory, compared to, the mean estimates across replicates, kind of that variability comparison. So if you had any comments on that, I was really curious about that. Thanks.
Oh, so regarding the computational demands for MCMC, so it's really related to Castle, which again, is it's pretty old software package compared to many of the other, software packages that have been used for this workshop. And among many things, the implementation of MCMC is quite cumbersome and not efficient. And what we've noticed is that when we've moved to Castle 2, when we've run some tests for the assessment next year, is that we've decreased like the time for MCMC by 13 times. So it's, in our case, it's mainly related to the software. This being said, even with Castle 2, I think it will take quite some time to implement MCMC, but I'm aware of some research that has been done in Seattle to find, better algorithms than the Metropolis Hastings, that are, both faster but also more accurate. I think it's a U-turn method, something like this. Like it's some research by Cole Monahan. Jim Sorson was also involved, and so probably it would be interested for spatial stock assessment modelers to look what has been done recently in that space to see if those better and faster algorithms could be implemented in the stock assessment software packages.
Yeah, thanks, Arnaud. And I got a follow up, but I'm gonna hold off on that because I saw some other hands go up. Bjarki, did I see your hand up, or maybe you took it down?
I did take it down, but I'm just wondering about that package that you were talking about. Is that the TMB stand package, or I remember seeing something about that a couple of years ago? Sorry, I haven't been following up on the patient front of things, but I was just wondering if that's the package you're referring to.
Oh, the ATM is something different, but it's interesting that you mention it because I would have thought that some workshop participants would have picked the ATM that Jim Sorson and Dan have developed. But that's something different. I was more talking about algorithms that are used in MCMC. I think probably we should pay more attention about what has been done recently to produce better, faster algorithms and try if we could just replace the classical algorithm that we use in your stock assessment software packages like Metropolis Hastings with those faster and better algorithms. And I think like I'm thinking about an algorithm that is called the U-turn algorithm, but there may be others. So it's maybe worth digging and just like reflecting on this issue.
Yeah, thanks, Arnaud. Jeremy, and then Valerio.
Yeah, just mentioning Castle 2, and it's a shame Craig, Marsh, and Alistair aren't here, which we're really doing a lot of driving in terms of improvements in Castle 2, but that's been a big focus for them and us in Castle 2 is to looking at improvements, particularly in MC improvement and performance. Some of the things that we are looking at, I know that the no U-turns approach, Alistair's been implementing that in the code base for Castle 2 and other ways to improve search spaces and MC algorithms. The other thing that Castle 2's got a lot of input into now is transformations of parameters. So to try to avoid correlation between parameter space. So there's a whole feature in Castle 2 around transformation, parameterization around estimable parameters. Yeah, that's been a feature in Castle 2 as to better performance in MC.
Okay, Larry, go ahead.
Can I? Can you hear me?
Yes, I can hear you.
I know maybe it's a bit late, but I had a very specific question. Maybe I should have raised before with the stock synthesis presentation, but I mean, I hope it's never too late. I think the Yellowfin tool dataset, I think is an interesting and very challenging example of sparse data. For instance, I think in the land distribution of commercial fisheries is probably one of the areas where us with the Gadget model, we have been struggling most. So data aggregation and resolution of fitting becomes a crucial decision to compromise among different axes of variability. For instance, time steps aggregating across different length resolution that those provided native from the operative model. I was actually curious to know, and I know, bear on me, I should have asked before, I'm a bit slow, but about the resolution of fitting that a stock synthesis group have decided for the land distribution, because the fitting was extremely good. And but it was presented at aggregated at I think over the old data set, if I remember correctly. And bear on me if I've just misunderstood. My question is the level of fitting of the land distribution presented over the old data set is a byproduct of a fitting still at a time step level, or is actually the data on the land distribution aggregated first, and then the fitting is attempted on the aggregated land distribution? So, in other words, is the fitting of the land distribution done for each quarter of the year, for each time step, or are the data aggregated first within the model before that likelihood component is fitted to the land distribution data for the fishery? Does it make sense? I hope it does, because the fitting was extremely good. Is extremely good, yeah. And I ask because, yeah, hopefully we can learn, and it can actually help us with moving forward with the Gadget fitting, where fitting the land distribution for each time step in the model with data which are so sparse is extremely difficult. I mean, yeah. Identifying those parameters for the selection curves is a hell of a job for the model with those data.
Yes, good observation. I was just going to open it up to anybody, and Rick raised his hand.
Sure. Yes, in synthesis, the fitting is to each observation, each quarterly observation. And indeed, they were quite sparse. And that does pose challenges with a big interaction between sparse data giving spurious recruitment signals, as well as contributing to estimation of selectivity. But the fitting is, as you were doing with Gadget, on the individuals. And, I don't recall if there was any particular difficulty, because it is averaged over a lot of observations, and they were able to get a fit that was consistent on when you summarize over all the observations, you do achieve consistency.
Thanks. Thanks.
Yes, please, Bjarki.
Oh, just a follow-up question to Rick or somebody who knows stock synthesis. The translation from age to length. I'm assuming that is that a log normal that translates the mean length, also the age distribution at length, and then you but that log normal has a time varying sigma or something, or how is the mechanics of this?
Sure, let me explain on that. First, the log normal aspect. There's an option to use a log normal distribution of length at age. I don't think it was used in this case, but it is an option. The mean length at age is interpolated seasonally from growth parameters. And so actually there's a feature to interpolate the mean size at age to a particular fractional date of the year. So if you have fast growing fish and you want to get a expected value for May 7th, you can do that even though it's within a season. So there is that generic capability that adds a good bit of complexity to the interior of the code. But in general, it's going to be fitting to the age length key that is at the midpoint of a season. Unless you invoke going to specific dates, which causes a lot more calculation of age length keys and definitely a slower model execution.
Okay, so essentially there's, I'm just wondering how you get the bin sort of width. So because I'm guessing you're fitting to an age length key. Sorry, this is a bit late in the day. So when you're fitting to an age length key, then you have a uncertainty around that, or sort of you have a variation, or a distribution around that, and that distribution is that I assume that's time varying, or is that also?